operators in Verilog. So there are bitwise operator. What I mean by bitwise operator is these operators do bit by bit operations. So they take each individual bit and perform a Boolean operation on that. So these operators are, these are the symbols, and these are the type of operation. This is not, and, NAND, or, NOR, XOR, and XNOR. Let's understand this, how do they behave. Okay. So let's start with bitwise NOT. So let's say you have defined two wires A and B. You can write A as NOT of B. What this means is B is inverted and then given to A. So if B is 0, A will become 1. If B is 1, A will become 0. Simple operation. So since it's single, A and B are single bit, uh, it's just a single bit operation. But let's see what happens when these are buses. So let's say define a bus 3 down colon 0 and X and Y. And what you have done is X is equal to node of Y. Now these are buses, and this is where the operator is bitwise will become important. So operator will operate on each of the bit. Meaning of that is Y is 4-bit. On each of the bit, it will do invert operation and produce X. Okay, so your Y3 will become invert of X3. As in X3 will be inverted of Y3. X2 will be inverted of Y2. X1 will be inverted of Y1, and X0 will be inverted of Y1. So just by using this one line, you have created in hardware, you have created 4 inverters, and each of the inverter is happening on each of the bit of the bus. So that's why it's called bitwise operator. For each of the bits, it will do invert operation. It is happening on each of the bits of the design. So just by doing this, what we actually have created is 4 inverters. X3 bit is inverted of Y3. So invert operation is happening on each of these bits individually to create X output. So that's why it is known as bitwise operator. It will take each bit individually and perform a Boolean operation. Okay. Similarly, there is bitwise AND. So what it will do is it will do bitwise AND. So when the signals are single bit, it does not make much difference. Basically what you are doing is just doing a B and C, which means A is output and you are ending B and C. But when these are buses, the real picture of bitwise comes into play. So you have created 3 signals X, Y, Z, which are 4 bits, and we define X is equal to Y and Z. X is AND of Y and Z. This will create 4 gates, 4 AND gates. X3 will be AND of Y and Z3. So basically, individually, it is happening bitwise. So the operator is working on each bit bitwise. It will take bitwise of this, it will take each bit of this and do the operation. So that's why it's important to have these two of the same size. Otherwise, it will not work. So X2 is Y2 and Z2, X1 is Y1 and Z1, X0 is Y0, AND of Y0 and Z0. So by using this, you have created bitwise AND operator of each bit and creating this. Okay? This is the meaning of bitwise operator. Similarly, there are other bitwise operator as we talked about. There is NOT we talked about, and this is for NAND. Similarly, it will perform NAND operation on each of the bits. It will perform OR operation on each of the bits. This is NOR operator on each of the bits. XOR and XNOR. All these functions are bitwise. They perform bit by bit operation on each bit. Okay. So what is a typical usage of these bitwise operator? Of course, not is used to create a complement. Let's say you have function bus A, you want to complement it, you will just do not of A. Each of the bit will be complemented, so it is created used to create complement. What is the use of and? And is used for masking. Okay. For example, let's say you have a bus. Okay. You want to mask these two bits, first top two bits, but you want to extract lower level bits. What you will do is you will AND it with 0 1 1 0. Why? Because these two bits which you want to mask, you will put it as 0, but whichever bits you want to extract, you will put as 1 1. Now let's see what will happen. This 0 with this will, whatever at the top, wherever you have 0, when you do AND, it will become 0. So first bit will become 0 because this is 0. Then this is 1, whatever the values here, let's say this was alpha and beta, these values will appear here. And this is 0, so it will become 0. So whatever values you wanted to extract will come here. If this was 1 0, it will come 1 0. It was 1 1, it will come 1 1. So AND is used to mask and extract the data. And is kind of also you'd be used to force reset certain bits of a bus. Okay. So let's say you have this bus, whatever the value is, you want to force reset this particular bit. So what you will do is you will make other bits as 1, this bit as 0, whichever you want to force reset. And when you AND, what will happen is, because this is 0, this will bit will become 0 because of ANDing, and rest of the bits will be same as previously. So what it will become is, let's say this was alpha, this was beta, this was gamma, this was theta. So what will happen is this alpha, beta will stay the same. This will become 0, and rest of the bits, whichever bit you marked as 0 will become 0. So it will force a bus to become 0. Similarly, OR can also be used to mask and extract. The only difference would be, rather than masking it with 0, you will mask it with 1. Or force, or can also be used to force a set, similar to how we used it to reset, or can be used to reset also. XOR is used for selectively complement. XNOR is used for pattern matching. Okay, how do you match pattern using that? Suppose, let's say you want to check what is the value here, whether these two values are same or not. If these two values are same, your XOR will become 0. If these two values are not same, it will become different value. So XNOR is used for pattern matching. So these are the typical operation of functions. We can think of how these bitwise operators will be used. Inverter will be used for complement, and will be used for masking and extracting data. Can be used for force reset also, or can be used for force set. So these are typical usage of these bitwise operator. Of course, there are multiple more usage as well, but I'm giving you some examples. Then there are arithmetic operators. What are arithmetic operators? You want to do addition, the operator is plus, you can do a plus b. This is synthesis. So some of the operators, so far we have talked about whatever all the operators, they are synthesizable. Synthesizable mean tool can automatically convert those into gates. But sometimes these operators may not be synthesizable as well, and in those cases we have to handle that properly. So this is fully synthesizable. That means whatever you write as add, synthesis tool will be able to convert this into gates. If output is 1 bit, let's say C is equal to A plus B, as we know, right? As in, there can be carry bit also, then the carry is not captured. In case you want to capture the carry, there is a notation you can use. We'll talk about this notation in a little bit more detail later on, but you can see here is, in this case, what will happen is A plus B sum will go here, and whatever the carry is, it will go there. Typically, when you are adding 2-bit single bit number, in order to capture both sum and carry, output should be at least 2-bit. Okay, so let's say if X and Y are 4 bits, then Z has to be 5 bits in order to capture all the values, because there can be carry also. Now, important thing to understand here is how these are addition operator. And if you remember previously, we designed adder and half adder. And now we are able to just write that complex logic by just using one statement in Verilog saying S is equal to A plus B. Okay. Or we can say carry, carry and sum equal to A plus B. So how writing in Verilog or writing in HDL gives you a powerful way of writing your code without going in with a simple language which can be very, very complex logic. And synthesis tool will automatically convert this into Git. That is the power of using HDL. We designed a half adder and adder which can simply be written in one line in Verilog. And that gives you advantage of writing very, very complex pieces of blocks like iPhone, right? That is that power which hardware description languages like Verilog give you. Then there is other operator minus. C is equal to A minus B. This is again fully synthesizable. Again, as we know, if we know the basic, A minus B just means A plus minus B, where minus B is 2's complement. Again, C needs to be at, if these are 1 bit, C again needs to be at least 2 bits to capture borrow as well. And in typically, let's say if X and Y are 4 bits, Z has to be at least 5 bits to capture both the subtraction and borrow in case there is some borrow which is happening. Similar to addition, in addition there is carry, in subtraction there is borrow. In order to completely capture those values, there needs to be one additional bit which needs to be maintained. Then there is multiplication operator, which is star. This particular operator is not fully synthesizable. I'll talk about what are the cases when it's synthesizable, what are the cases where it's not synthesizable. In multiplication, in order to capture values, let's say if X and Y are 4 bits, then the multiplication at least has to be 2 times. It has to be 8 bits. Some cases of it is a synthesizable. Some cases of it's are not synthesizable. Typically, as in 2 multiply by 2 raised to power n is like shifting bits, then it's synthesizable. Similarly, division, it's not fully synthesizable. There are cases where it's sorry, I made a mistake. Multiplication is fully synthesizable. Division is not fully synthesizable. This is the symbol for division. If it is 2 raised to power n, then it's synthesizable. Synthesizable means tool will automatically be able to convert. Otherwise, it's not synthesizable, or you have to create division module yourself for synthesis tool to use. There is a modulus operator for calculating the remainder. And again, this is also not synthesizable at all. You have to create your own module to create a module. Then there is equality operator. Equality operator means you are checking whether two values are equal or not equal, and it will result in output value which is true or false or 1 or 0. Okay. So for example, you want to check whether A is equal to B or not. Then the value is your output will be either 1 if they are equal or 0 when they're not equal. A is not equal to B, you are checking, output again will be 1 or 0. If they're not equal, then output will be 1. If they're not equal, then 0. It can also be, equality operator can also be done on buses. So if you're, let's say, comparing two buses, when Y and Z are 4 bits, the output will still be 1 bit. Output will not be 4 bit. It is checking whether each and every bit of this Y and Z match, and then compare to it, this, and then the output will be 1. Compare this to bitwise operator, right? So we did a bitwise operator X or Z, where output will be same size. Output will be same. This was 4 down, 4 to 0. This was 4 to 0. Output will be same size, 4 to 0, but individually bit will be odd. Here, output will be 1 bit compared. So this is equality operator. Output will always be 1 or 0. Now what happens if you are comparing y equal to z? In case y is 1, z is 0, they're not equal, your output will be 0. If there are 1, 1, the output will be 1 because they're equal, and so on. What if you're comparing y equal to z? Verilog also supports value where y is x and z is 1, or y is z and z is 0. What will be the output in that case? How do we know? In that case, output will be x or unknown. Okay, if any in these equality operators, if any of the input is either x or z, then the output will be x. This is how these operators behave. Okay, now suppose you want to check equality when there is x also involved. There are then special operator which can also match x and z also. So the symbol for that, in this case you are using 2 equal to, you will use 3 equal to. You are using not and equal to, you will use not and 2 equal to. In this case, it will match x and z also. So let's say you have a and b. You are checking is a equal 3 times equal to b, and let's say a is x and b is 1, then the output will be 0 because they are not equal. But if a is x and b is also x, then output will be 1. But if you are using a equal to b operator, then in this case, output will be x. In this case also, output will be x. For this operator, as long as one of the input becomes x or z, the output will be x. But here, using 3 equal to, you will be able to compare exact x values also. So if both inputs are x, then it will become 1. This is typically only used for simulation. Because comparing x does not mean anything in real hardware. This is just typically to use in simulation to check certain conditions. It has no meaning in real hardware. So it's only simulation specific construct which can be used for verification, but it has no meaning in hardware.